Okay, hi everybody. We're going to jump into finishing the lab. One thing that you should have is you should have your height data. I don't have this filled in. I'll grab a sample piece of data. And we should have the displacement in meters. For this table, that is the compression distance of each notch on the marble launcher. So some teams may need to finish this table here, which is going to be using the height values to calculate potential energy. From that, get the velocity of the ball as it left the launcher. Then compare that to the actual measured velocity, which would be the value that you get from the sensor that you attach to the end of the launcher. So we'll go to this, and I'm going to grab real quick just a piece of data. We'll use 0.18 for a height value. So the first thing we'll do is look at our potential energy, which will be mg delta h. And the potential energy here, we would need to use the mass of the marble, which is escaping me at the moment. You'll have to confirm this, but I want to say that it's somewhere in the range of like, I don't know, 10 grams or something. Let's just pretend that it is. So our mass would be 0.01 kilograms times 9.8 times a height of 0.18 meters. And that gives us a potential energy of a value. So 0.01 times 9.8 times 0.18 will give us very small, not a lot of potential energy here, and that is 0.01764 joules. Again, I don't remember the exact value of the mass, so if your kind of mass number, which would be here, if that is different, which I'm assuming it is, if it's a different order of magnitude, like it's not 100 grams, and I don't think it's less than 10, so it should be somewhere in this range, but again, we're just sort of pretending for the moment. Now, to get the velocity, this actually comes from the fact that this system is a conservation of energy system, and we're looking at how the kinetic energy of the ball basically turned into the gravitational potential energy that corresponds to the maximum height of the marble, which is what you determined. So the kinetic energy formula being 1/2 mv squared, for this exact example, we're going to use the value of the potential energy that we saw calculated like right above this, and we are going to use the same mass for the same ball, and that's 0.01 kilograms equals 0.01764. We'll divide by 1/2, and that will get us to 0.01 v squared equals 0.03528. Divide by 0.01. That gives us a v squared of 3.528. Then we have to take the square root of that, and that would get us our velocity of 1.87, let's call it 1.88 just for kicks. Go away, malware bytes. Meters per second. So there you go. That's your velocity that you would have calculated. And let's go ahead and say that the v calculated. And just for the sake of it, let's do the measured velocity. Go away. Let's say that it came out to be 1.75 meters per second. To do that percent error, the percent error is essentially like how far off was your calculated value from the legitimate true value. The sensor itself is going to give you the correct number for the velocity because it's directly measuring it. So we're going to compare those two things. So the percent error is going to be the calculated value, 1.88, minus the experimental, calculated value of minus the actual, I don't know why I wrote an M, and that's 1.75, absolute value of that over 1.75, which is the actual value, and that's going to be times 100. So if we do that, we'll do 1.88 minus 1.75, giving us our next line, if we're kind of doing this piece by piece here, 0.13 over 1.75 times 100. And continuing that, just going to do both of those at the same time. Then this would give us a percent error of 7.4, let's call it 7.43%. And that's pretty good. That would not, if that was a real piece of data that you took, that would be very good, 7.43%. For this type of experiment where we're trying to figure out the height via a slow motion video taken with a phone camera on a meter stick where you might not be able to even see the millimeters, this isn't bad. Now that we have that squared away, we're now going to look at the spreadsheet and what we're doing with that. So as far as the why of this, like what is the point, that would kind of bring us back to what are we trying to accomplish with a graph like this? And essentially, if we're making a graph, right? We have a y and an x-axis, and we know that the way that a line graph works is that you have your y-intercept, which is b, and then your slope is, we represent it as m. And the sort of standard slope-intercept form is y equals mx plus b. So the power of using a graph in science in general is that the slope of a line is a very easily calculated number. It is not hard at all to calculate the slope of a line. And so what we can kind of do with this is say, okay, we can use algebra equations to represent how real objects move, interact, whatever. So if we take the equations that govern whatever our scenario is, and we sort of squish them around until we make a graph that looks the way that we want it to, we can sort of force the graph to have a slope that is representative of a number that might be relevant to us. So how do we figure out what that is? Well, we know what information we have is the height. That's the actual data that we took. And that corresponds to gravitational potential energy. Then, where does that energy come from? It comes from the spring potential energy. So the energy equation here would look a lot like this, or I guess exactly like this. We would be starting with spring potential energy and ending with gravitational potential energy. Spring potential energy is calculated with 1/2 kx squared, where k is the spring constant and x is the compression of the spring. And gravitational potential energy is mg delta h. So let's think about what things we have. We have h, we have g, that's a known value, we know the mass, and we know our x values. Those are just measured from the spring launcher. Therefore, the thing that we would like to know is what is k. So what we're going to do is I am going to walk you through this. We're first going to swap these around. And it'll hopefully become clear why in a second. But we're going to swap these around and change that. So mg delta h equals 1/2 kx squared. And if we kind of bring that back up here, or actually I'll bring this down, I'm sorry. Get a little, here we go. Y equals mx plus b. So there's our standard slope-intercept form linear equation. And kind of what we do now is we get to, I guess play around is the wrong word, but we as the sciencey people get to choose essentially how we would like to construct our graph. What are we going to plot as our independent variable? What are we going to plot as our dependent variable? And so we should ask the question of, well, in this actual experiment, what is the independent variable and what is the dependent variable? And so the independent variable in this experiment is very explicitly x. X being the compression distance. That is the independent variable because that is the thing that we are actively controlling. And the dependent variable is going to be the height. Because the height that the ball reaches depends on how far we have compressed the spring. So that sort of tells us that if the independent is typically on the x-axis, and I'll write that here. So the independent is on the x-axis, and the dependent is on the y-axis. Then we should think about, okay, what now? The trick for this is that, and if you do more science, you'll learn more of the rules about what you can and can't do. You may, look back on this lesson 5 years from now and yell at me for doing bad science. That's fine. I'm just sort of introducing you to the idea and making this as easy as we can. So here's what we're going to do. We are going to line up certain parts of the equation that actually is the physics equation that governs how the system works with parts of the linear equation that is the slope-intercept form. So if we line up the y-axis, which is the dependent, with mg delta h, and we line up our independent, our x-axis, with x squared, then by definition, that will allow the slope of the line to equal 1/2 of k. This is not exactly how one might do this properly, but it works fine for us. One thing we can say is that we do not have a b, so we don't need to worry about that. So why? Why do this? Essentially, the reason is, now that we've sort of figured this out, what this tells us is that if we put the x squareds here and mg delta h's here, then the slope must be equal to 1/2 of k, because that is how the actual physics equation works. It is 1/2 of k, it lines up with m, if mgh is y and x squared is x. I know there's two x's there. I know that's confusing, but x in the physics equation is compression distance, and x in the standard slope-intercept form is the x-axis. It is nice that they line up. But one thing to note is, and this is worthwhile talking about, it is totally fine for you to graph x squared as your horizontal data points. That's totally fine. All you have to do is square the compression distances and then use those numbers as your sort of coordinates. So what this would kind of end up being is we'd have our sort of table of ordered pairs. That looks terrible, but you would have as your x and your y, you'd have your x squareds and your mg delta h, and you would sort of fill in the numbers, which is what we're going to do in Excel, and then have Excel do the graph for us. So if we go back to Excel, or go to Excel, I've just grabbed some kind of data on the height values. You're going to put in, to make your table look like this in Excel, just literally set it up exactly like this. And your first 5 data points, these are your 5 heights for notch number 1. These are your 5 data points for notch number 2, and these are your 5 data points for notch number 3, whatever those look like for you. Then for the x values, this is the compression distance squared for notch number 1, and this value is actually going to be the same for all of those. So you're going to have basically 5 copies of the same sort of data point for those x values, which are the x squareds. Then for the y values, we need m times g times delta h. And to do that, instead of doing hand math, we're going to get Excel to do some math for us. If we have more time later this year, we'll focus more on this. But for now, to tell Excel to do some math, because it can, we're going to write a formula. Now, writing a formula in Excel is different than writing a formula by hand. We're going to start with an equal sign that says, hey, Excel, do some math. Now we need to type m times g times delta h. We'll use the actual value of the mass. Again, I'm not sure what the actual value is. I'm going to use 10 grams, which is 0.01 kilograms. Your number may vary. Then times 9.8, that's g. And then multiplied by the height. And so for the height, we want to write this as a formula because instead of typing in the number every time, we'd like to have Excel do that for us. And how this works is we are going to tell Excel, hey, look at this box, this cell, and whatever number is in that box, use that here for this math. And so we need to pick the correct height number. We want this one here. So this one, we can do this one of two ways. You can either click it, or you can type the cell reference. Notice that it says B2. That means column B and row 2. Talks about this box. Once you have this, you can click enter, and it will calculate that value for you. Now we do not have to calculate or type that in again. We can simply hover our mouse right here until it turns into a plus sign. Click when it's a plus sign, drag it down, and lo and behold, it will automatically calculate those values for us. And what's nice is that when you do that, it references the correct box. So this one is B2, this one chooses to look at B3, B4, B5. You can see it changing right here as I go down. B6, 7, 8, 9, 10, 11, you get the point. Now we are going to make our graph. So we'll highlight our data and make a graph. We do that by going to Insert. Over here is Charts. Click on the scatter plot looking one, and we want a standard old scatter plot. This is perfectly fine. Zoom out a little bit. And now we need a couple of things. We need to give ourselves some axis titles. We need a line of best fit, which they call a trend line. And if I did that a little fast, if I click the sort of options up here and I go to trend line and I click this little arrow, it gives me another menu within a menu, click more options. You want it to be on this bar graph sort of menu here. We're going to scroll down and do a couple of things. First, we're going to set the intercept to 0, 0 because of the actual reality of this situation. If we do not compress our spring at all, we should get no height because it's not going to do anything. So we're going to set our intercept to 0, 0 and click display equation on chart. And that, dear friends, is it. This number right here, so this slope, right, y equals mx, the slope was 1/2 of k. So if we're looking at our graph, this is the slope. That means that k is twice this number. And if we do that, we see that the spring constant of this spring would be 43.4 newtons per meter. We're going to want to label our axes. So the axis title here is going to be, so the horizontal data points were x squared, which is in units of meters squared. No, that. And then this one is gravitational potential energy in joules. And then our overall title would be we would have potential energy versus x squared for, we can do whatever we want here, for a spring launcher. This is fine. So once you have this, this is pretty much it. You would then take your slope here, multiply it by 2, and then that is going to be how you wrap up this document. You put your spring constant in here, which based on my experiment is 43.4 newtons per meter, as that was twice the slope of my line. And that is it. Hopefully that's enough to kind of get you where you need to go. Submit this by whatever time I set the Canvas assignment to close. And don't forget to do your test. Okay, Toodles. It is done.